Okay, welcome back to differential equations. Today is lecture 5. We're talking about initial value problems. So people abbreviate this with IVP, so you'll see that as well. So the idea is that now we know how to solve some differential equations. We know how to check some solutions. But what we're going to add on to that is we can solve the differential equation while imposing additional conditions. So this means something specific, which we'll get to. But the idea is that you impose a condition on your solutions. So you might have noticed that when we solved these differential equations so far, we keep getting these one parameter families of solutions. So the idea is like, well, what if I don't want all possible solutions? That's what the parameter is telling me, or it's telling me just like infinitely many solutions, maybe not all of them, but a bunch of them. What if I just want like one out of that family? That's what this does. That's what this helps us do. Okay, so let's see an example, and this comes in handy in real life applications, which we'll get to next time. Okay, so an initial value problem looks something like this. So you say the differential equation you want to solve, and then you either list or you can write the word subject to, and then you write your conditions. So we're going to solve this differential equation subject to this additional condition, which I'll write like this. Now, what does this mean? We have to remember what this type of thing means. Well, what this means is that I want, when I plug in 0 for x, then I want y to be 3. That's what this is saying. And so what we're really saying, i.e., our solution, whatever our solution that we get, which is usually a one parameter family, it should go through the point 0, 3. So when you have a one parameter family of solutions, you have a whole bunch of solutions that range depending on your constant. But now we want a solution that also does something else, which goes through a point. Okay, so let's see how this works by just solving it. So this is separable, made it nice and easy, so we can do it quickly. We just have to change it to dy dx and divide the y over, and then integrate on both sides. Integral of 1 over y is y equals x plus a constant. This one we can do e on both sides to get y alone, and then we can rewrite e to the c as just c. So that's what we're doing here. E to the c is becoming c. Okay, so in any case, this is a one parameter family of solutions. So this is what we learned how to do already, to the differential equation. But a solution to the initial value problem means I have to now take my one parameter family and make sure that it goes through the point 0, 3. So how do I do that? What does it mean for the graph of a function to go through a point? It just means that when I plug in x equals 0, y should be 3. And that means it goes through that point. So all I'm going to do is now use this initial condition. And what that means is I'm just going to change my y to 3, my x to 0. And then what we'll see happen is our constant will be chosen for us. It's no longer just an arbitrary constant. It's going to be a specific number. So e to the 0, that's just 1. So 3 equals c. So what this means is that when I plug this c back in, well, it is one of the solutions in the family, it's the one with c equals 3, but it's also the one we want because it's the one that goes through this point. Because when I plug in 0 for x, I will get 3 for y. So we say that this solves the initial value problem because it solves the DE and it obeys the extra condition. So it's not so bad. Okay, so it's the only member of the family of solutions going through 0, 3, i.e. obeying the condition y of 0 equals 3. So one thing to notice, this pattern will keep happening, so it's good to point it out now. If I impose a condition like this, y of, I plug in one number and I get another number. So that means x equals a, y equals b. Well, that's the same as, it's the same as saying that the graph goes through. So this is just pre-calc knowledge or algebra knowledge. Plugging in that x and that y is the same as going through that xy coordinate. But then now, the way we want to think about it is that it specifies, picks a member of the one family parameter of solutions. Sorry, one parameter family solutions. But what that really means is it really just picks a specific constant. Instead of just leaving it as C, it's going to pick the constant. So if I pick a different initial condition, initial value, so initial value problem, like this, so it's the same differential equation, but my condition has changed. Well, that just means that I'm going to be solving for C again. Where the solution, the one parameter family is the same because it's the same differential equation. So that's going to be the same, but now my C is going to be different. So this new condition is saying to pass through, I plug in 1, get -2 as my answer. So -2 equals C e to the 1. I can just divide by e. That's my new constant. So then y equals, now I plug it back in, is the solution to the initial value problem. That's it. So we should really remember that imposing a condition, really what it does is it just picks out a specific constant in your one parameter family. That's going to keep happening. So far, we've only ever had one constant in our solutions. So we've only ever dealt with one parameter families, but you can have 2 parameter families or 3 parameter families, meaning you have multiple constants in your solutions. And then we'll see that our initial value problem works very similarly with a slight modification. Okay, so far, we've only solved differential equations that had first derivatives, meaning there was a y prime, but there was never anything higher, like a second derivative or third derivative or so on. But there can be higher derivatives in your differential equations. And what will happen is that solutions will have more parameters. So we'll see how to solve things like that later. But for now, we're just going to impose conditions on solutions that have more parameters. Okay, so can impose more conditions. So let's just see an example here. So we're just going to impose that, and then we're going to think about what it means. Y of pi over 2 equals -2. So real quickly, we already know what this really means. This means that pi over 2 comma -2 is on the graph of the solution. But we're also going to impose something about the derivative, y prime of pi over 2 is going to be 1. So what is this saying? This is really just saying that the slope at x equals pi over 2 is 1, meaning the slope of the tangent line, or how fast the graph is going up, should just be 1 at pi over 2. Okay, so we're going to impose these conditions on y equals a cosine of 4x plus b sine of 4x. So the idea would be like we already solved some differential equation. And this was the solution we got, and it had 2 parameters. And now we're doing an initial value problem. So we're imposing conditions. Okay, so I'll just say which DE it comes from. Y double prime plus 4y equals 0. So we don't know how to solve a differential equation like that, but we do know how to check. So you could check that this is a solution, a 2-parameter family of solutions, and it is. Okay. So let's impose these conditions. So what do we want? We want y of pi over 2 to be -2. So that means I have to look at this solution and make sure that when x equals pi over 2, y equals -2. So I just have to impose it by making that happen, changing my y to -2, changing my x to pi over 2, and then let's see what happens. Oops, I changed that to a cosine. That should be a sine. Okay, so we got to remember some trig. So what is, this would just be 2 pi now. What is cosine of 2 pi? That's just a 1. And sine of 2 pi is 0. So actually this condition tells me what a is. It tells me that a is -2. So this is saying that if this is a 2-parameter family of solutions, that means that I can change a and b to whatever I want, and it'll still solve the differential equation. But if I really want my solution to go through pi over 2 comma -2, then I have to change a to -2 specifically. So y equals -2 cosine of 4x plus b sine of 4x goes through the right point. But then notice, now it's a 1-parameter family. Of solutions. So as b varies, ranges between numbers, I'm going to get lots of different solutions to the same differential equation going through this same point. So now the idea is I have pi over 2 comma -2, and I have lots of solutions that go through that point. So I don't know how they look. I'm just going to like randomly draw lines here. But the point is I have lots of solutions that go through that point. But now I really want the derivative at pi over 2 to be what was it, 1? So I really want a solution that has a tangent line with slope 1. And so there's lots of these other solutions that go through the right point, but their slopes are not the right slope. Okay, so actually imposing this condition is not so bad. It just means I need the derivative so that I can plug pi over 2 into it and set it equal to 1. So what's the derivative of this function? Let's see. So I guess I have to rewrite it here. So I already know a is -2. So -2 cosine of 4x plus b sine of 4x. Okay, so the derivative, well, derivative of cosine is negative sine. So this will become positive 8 sine of 4x. Derivative of sine is cosine, 4b cosine of 4x using the chain rule. And then now, when x is pi over 2, I want y prime to be 1. So I'm going to impose that condition by just plugging it in. And this will allow me to solve for b, as we'll see right now. So this is sine of 2 pi again, so that's just going to be 0. And then this will just be 4b because it's cosine of 2 pi. So b is going to be 1/4. So this means that y equals -2 cosine of 4x plus 1/4 sine of 4x obeys both conditions. So it'll go through the point pi over 2 comma, what was it? The point that -2, yeah. It'll go through pi over 2 comma -2, and its derivative at pi over 2 is 1. So you would also say that it solves the initial value problem. Okay. So let me just say it in that way too. So if I said solve y double prime plus 4y equals 0, that was the original differential equation. Subject to these two conditions, then the solution would be what we just wrote, be this thing. And something to take away is the fact that I needed two conditions to get two constants or parameters, to specify precisely two constants instead of keeping them as arbitrary. And when I only had one condition, the other parameter was still arbitrary. So I still had lots of solutions. Okay, so that's basically how you solve an initial value problem. You get the arbitrary solution, which for us is usually a one parameter family, but I could just give you a solution to a higher order differential equation. And then you use the conditions to determine constants. And there's a lot more to be said about this stuff, but constants. But we'll bring it up as we need it. Okay. That's all I want to say about that for now. Maybe we'll come back later when we do applications. The next thing I want to talk about is just sort of like this little extra thing that we haven't worried about yet, but actually is important. So we also care about something called an interval. We also care about determining intervals for solutions. which means we're really just asking, like, where do the solutions make sense? So for example, you can check if you like 1 over x, y equals 1 over x is a solution to the differential equation x y prime plus y equals 0. So you can check that if you like. But you might remember something about this thingy. So if you look at it as a function and you try to graph it, it looks like this. And it's got an asymptote at y equals 0. And so it's undefined at y equals 0 is another way to say that. So even though it's a solution, we have to think about that a little bit. So it is a solution to the differential equation, but this thing as a function, just in a vacuum as its own thing, is not, the fancy word is continuous at 0. It's also not differentiable, another fancy word, just means it doesn't have a derivative there. At this level, that's what that means. So when we say that this is a solution, we have to be a little bit careful. It's not always a solution. So we have to say where it's a solution as well, because it doesn't solve the differential equation if x is 0. So when we say y equals 1 over x is a solution, we really mean it's a solution on any interval not containing x equals 0. So not on, for example. So what are intervals? So intervals are confusing because they look like coordinates, but this means all the numbers from -3 to 5, not excluding -3 and 5. So for example, if I go from -3 to 5, so I'm just zooming in only on this portion of the function, well, that's not then it's not a solution because it has this bad point 0. And so what we want to do is we want to say the biggest intervals where it is a solution instead. So we would say y equals 1 over x is a solution on either -infinity to 0 is fine because that means I'm not including 0. So -infinity to 0 means I'm only looking at this side of the graph. And then, so that as an interval is good. It is a solution on that interval. Or you could also do 0 to infinity, the other side, because neither of those contain 0. So you could also just zoom in on the right side only, and that would be fine. So this is something we haven't done yet, but so we've just been saying solutions without worrying about if it's defined the whole time or not. Okay, but it is something to think about. So here's one more example. And we can combine what we just did with parameters and initial value problems. So for example, this thing is a 1-parameter family of solutions to the differential equation. So you don't have to check it, but you can if you want for practice. Oops, y prime plus 2xy equals 0. So this will work for any c that you plug in. it'll be a solution. But now, if I say like solve the initial value problem, then we have to think a little bit more. If I say solve the initial value problem with this differential equation subject to y of 0 equals -1, then what's that going to do? Well, it's going to pick out a specific constant for us. And once we have that, then we'll have an undefined point perhaps on the bottom. So let's see if that happens. Okay, so we know how to do initial value problems. We already know that this is a one parameter family of solutions. So now I just got to impose this condition. So let's do that. C will be -1. So that means what solves the initial value problem is this. But on what interval? Well, we can factor the bottom out. And then we can see that at 1 and -1, there's going to be undefined points. But everywhere else is okay. And just for, you don't have to remember how to graph it, but just for, it'll help if you do, so I'll just do it. So the graph looks something like this. And then here is 0, -1. So on what interval is this a solution? Well, now we have to be a little bit careful. So before, up here, we just said, I just got to avoid x equals 0 because that is a undefined place. So -infinity to 0 was fine, but so was 0 to infinity. Here, we don't actually have a choice. So you might be thinking, it's good over here, we're good over here, and we're good over in the middle too. So if it wasn't for the initial value problem, that would be true. But I need my solution to go through the point 0, -1. So the interval of solution to the initial value problem is the one containing 0, -1. So it's really just this interval from here to here, because I can't jump over this break at 1 or this break at -1. So it's just from -1 to 1. So see here, this is 0, 1 is a point, and then this is the interval. So the notation is a little bit annoying. But yeah. Okay. So the interval of solution to this initial value problem is -1, 1. Not, for example, -infinity to -1. And I also can't do 1 to infinity, meaning I can't do these two because they don't contain the point. But if I took away the initial value part, if I just didn't care about imposing this, then I could use the other intervals too. So if I just said, name the biggest intervals where y equals 1 over x squared minus 1 is a solution, but I didn't say solve that initial value problem, then I could be negative infinity to a -1, or -1 to 1, or 1 to infinity. It could be any of the biggest intervals not containing the undefined points. But if I say solve the initial value problem, then only the interval containing 0, -1 is the correct one. Okay, so we just got to keep that distinction clear. Okay, so with practice, this stuff will be a bit easier too, so don't worry too much about it right now if it seems hard. Okay, so see you next time.